All right, we're continuing on here with our Chapter 9 videos, and we're going to move into talking about covalent bonding now, and then in a little bit we'll talk about bond enthalpies. Okay, but covalent bonding, different from ionic bonding in that we are sharing electrons instead of transferring them. Okay, so if I have, for example, Lewis dots for a pair of fluorine atoms, and fluorine has 7 valence electrons, so I'll have 7 dots for each one. Okay, so both of these want to satisfy the octet rule, so they both want 8. Right, that hasn't changed. So, but rather than transferring an electron from one to the other, because if we did, one would have 8 and the other would only have 6 now, what they're going to do is they're going to share electrons so that each one feels like it has access to another electron. Okay, so each one of these fluorine atoms feels like it has access to all 8 of these electrons. Okay, and the other fluorine also feels like it has access to all of these electrons. Okay, so those electrons that they're sharing, it's kind of like joint custody. They both get to have access to them. So if I do a different example, let's look at a pair of oxygen atoms. Oxygen has 6 valence electrons. Okay, again, we're going to try and get to 8, and in order to do that, each one needs access to 2 more electrons. Thankfully, they each have 2 electrons to share. So they're going to share this pair, and they're going to share this pair. All right, so if I draw this in a slightly different way, I move those electrons right between the 2 oxygens. Okay, so both oxygens feel like they have access to 8 electrons. Okay, and the way we typically will draw this, rather than having dots in between, we will draw those shared electrons as lines. Okay, and each line represents 2 electrons. So we can almost imagine that each electron sits at the end of each line. Okay, let's take a look at another example. So that we saw one example with fluorine having 1 bond. Now we have an example of oxygen with 2 bonds. Let's take a look at an example of something that makes 3. So if I have 2 nitrogen atoms, each one of those has 5 valence electrons. All right, both of them need another 3 electrons to get to 8 electrons. So each one has 3 that they can share that are unpaired. And so we're going to share 3 sets of electrons. That way each nitrogen feels like it has access to 8. Right, and that's the point of the sharing of electrons, is that each one has access to enough electrons to satisfy the octet rule. So drawing this with lines instead of dots, I'll have 3 lines representing 3 shared sets of electrons. right? So we have our three examples. We have our triple bonded nitrogen, we have our double bonded oxygen, and we have our singly bonded fluorine. Right? So single, double, or triple bonds have different lengths and different strengths. So bond length and bond strength are something that we can begin to talk about. So triple bonds are the shortest and strongest. Right? Double bonds are longer and weaker. And single bonds are the longest and weakest. Right? So the triple bond is the shortest, strongest bond. Okay, we can also talk about bonds in terms of what is known as bond order. Okay, and in the next chapter, we're going to use bond order more extensively in terms of how to calculate a value for it. But to sort of introduce you to it, we can calculate bond order by the number of bonds divided by the number of bond areas, regions of bonding. Okay, so an example that we will take a look at in the next chapter would be, for example, what is the bond order for carbon dioxide? Okay, so I have a total of 1, 2, 3, 4 bonds. So bond order, 4 bonds, and there are 2 areas where the bonds are. So those are the number of bond areas. So I'll have a bond order of 2. That corresponds to double bonds. Okay, so let's look at some of the things that we've just been doing. So if I have, for example, fluorine, all right, so fluorine has a bond order. The number of bonds is 1. The number of bond areas is also 1. So we have a bond order of 1. 1 is the bond order for single bonds. Right, our oxygen the bond order, we have 2 bonds. There's 1 bond area, so we have a bond order of 2 for double bonds. And our third example was nitrogen. Our bond order, we have 3 bonds. There's 1 bond area. So a bond order of 3 corresponds to triple bonds. Okay, so bond order is also related to lattice energy. So triple bonds will have higher lattice energy. Single bonds will have lower lattice energy. All right, and we can think about that in terms of what we've already discussed with lattice energy. So fluorines are both 1s, have charges of 1, and they're very small. Oxygens have charges of 2 and are slightly larger. Nitrogens have charge of 3 and are slightly larger. So with that increase in charge, that relates to lattice energy. All right, so let's go into a new topic, and let's talk about bond enthalpies and how they can be related to delta H of reaction. Okay, and what we're going to do is we'll use Hess's law. Okay, and Hess's law says that the individual enthalpies of a process can be added together to get the enthalpy of the process. All right, so bond enthalpies are given in tables. This is very important. Okay, and what you'll see are lists of a particular type of bond, let's say an HF bond or a CO bond or something like that, and there'll be an associated enthalpy with that particular bond. In order to calculate delta H of reaction, we very simply take the sum of the delta H for bonds broken minus the sum of the enthalpies for bonds formed. Okay, now you can also do this broken plus formed, being sure to flip the sign on formed energies. I think it's simpler to just say broken minus formed and not have to think about flipping signs. Okay, so let's take a look at an example and see how this works. So if I have a reaction that is hydrogen gas plus fluorine gas, gives me 2HF. Okay, now the easiest way to approach this is to draw a picture of each molecule. So I have a hydrogen bonded to a hydrogen and a fluorine bonded to a fluorine, and they make two hydrogen fluorine bonds. Okay, so in order to make my two HFs, I need to break that HH bond and that HF bond, and I'm going to make each of these HF bonds. Okay, so the enthalpy of the HH bond is 432 kilojoules per mole. The fluorine-fluorine bond is 159 kilojoules per mole. And each of the HFs is 565 kilojoules per mole. All right, so we make the moles disappear from our units because we're going to multiply by however many moles of molecules that we're breaking, moles of bonds. Okay, so in this case, I have 1 mole of hydrogen bonds that we're breaking, 1 mole of fluorine bonds that we're breaking, and 2 moles of HF bonds that we're forming. Okay, so 432 kilojoules plus 159 kilojoules. Okay, these are our bonds broken, sum of the bonds broken, minus 2 times 565. These are our bonds formed. Okay, so when I arrange it this way, I don't have to think about trying to flip the signs for forming bonds. And the result will be a negative 539 kilojoules, which is our delta H of reaction. Right. I'm going to go ahead and stop this video right here. We'll come back with the next video with another example of this process, and we'll continue on from there.